So, welcome back. Topic 14 of our lecture on concurrent programming will be full of action. We are going to put CCS into action. And we start with a review where we have been standing. Namely, you have seen full CCS. So you have seen the syntax, you have seen the semantics, and you have seen that the semantics is sometimes a bit nasty, and it can be made less nasty if you restrict recursion to not run over static operators, which means that when you look up something by this partial function gamma in your semantic rule, in particular in this one, you will not pile up static operators. This is a static operator, this is a static operator. The other are dynamic operators. What is the difference? The difference is they disappear by taking a transition. They are no longer there when you take a transition. But these are here. Here, right? So the operators remain. The operators remain after taking a transition. And if then recursion kicks in, they may actually pile up, right? And in order to avoid that, we have introduced regular CCS. And if you make sure that this partial function is maps on regular expressions, then all is fine. Okay, so that was the status. Now we want action. Okay, and we are gonna get to the action by playing around with some buffers. Let me first explain you what a very simple buffer is. What we have here is a buffer. This is a buffer which is able to accept that someone puts something into it, right? And then with get, it can be taken out. Okay? So what you have actually seen now is this very simple specification in action. So you have seen a buffer. Okay, and the buffer, what it can do, it can accept a put and it can accept a get. And it gets you this kind of very simple behavior. This is what we have seen so far, and the transition system is this, right? With this one being the initial state. Now, question, is this a regular CCS expression? The answer is yes, this is regular. Now, what else can we build? Here's another one. This one now says, wow, you can put something in, and then something is in the buffer. And then you can put one more in, you can get it out, or you can get it out directly, but then you can put it back in. Now, we should try to see the semantics of this one. Here we have it. So, and what we see basically, if we look at the semantics, we see that we can do a put, and then, okay, we can do another put, like in the first line, or we can actually do a get and we are back to the original. So this is now the behavior, and you can view this as if you want, a two-place buffer. So it can store two things in a row. We can put one in, right? Initially you can put one in, you can take that out, or you can put one more in, and then you can take that one out. Well, then you can put one back, or you can take the second one out, right? So this is a two-place buffer. I have another version of a two-place buffer. Here it is. So here we have a two-place buffer that actually has the same behavior. Let me just show you that this is actually the same behavior. If you just look at the transition system, it is isomorphic to the one that we have seen before, right? And how is this one built? Well, it's built basically in a way that you can put one in, you can put another one in, then there are two in there, or you can take it out, then there is 0 in there. So you see that the index is basically an indication of how many are there. And of course, you can, with this, you can now build 10-place buffers if you so like, right? I guess you understand what I'm trying to say. And if you want, we can look at the behavior of this system also from the perspective of what actions sequences can be built. And you see it, there basically is a put, a get, well, maybe there are two puts because we are filling two places, and so on and so on and so on, right? So this is what is possible here. So very long and not very interesting. basically this is the sequences that you can build out of this one.
So what you have seen so far is this one, and the semantics was this transition system, the reachable fragment, and the initial state was the buffer, right? And now, interesting question, is this a regular CCS expression? And the answer is, indeed, it is regular. There is no recursion over static operators. Then we have seen this one, right? You remember? And with this behavior, and that one being the initial state. And again, the question, is this regular? Answer, yes. Third that we have seen is this one. And as I say, if you duplicate this line, replace the 1 by a 2, the 2 by a 3, and the 0 by a 1, and you then write this line below with a 3 here and a 2 there, you have a 3-place buffer. Now you have a 2-place buffer. Starting here, you have a 2-place buffer. And again, this is a regular CCS term. None of the terms here uses any static operator, so it's not super surprising that it's a regular, that they are all regular. And I think it's easy to see that given that this is the initial state here and this is the initial state there, these two are isomorphic. But of course, this one is not isomorphic to this and to that. Now, let's move one step further. And now we are going to consider two parallel buffers. Now, what does this mean? We take the original simple buffer, this one, and we put two of them in parallel. Let's first have a look at the intuition.
Now here we have two buffers, and we can put something into one, into the other. The order doesn't matter. And then we can take it out of this, or we can take it out of that, right? So there is a put here, a get there. There's a put here, there's a get there, or there is a put, and a put, and a get, and a put, and a get, and so forth, right?
So what I've actually shown you is this, right? You have two buffers and they're independent. They can do put, get. And once they've done that, they are again able to do put, get, and so forth. So if you look at a random generated path, you see put, get, get, and so on and so on and so on, right? And now the question is this a two-place buffer? Well, what do you think? Should be, right? I mean, there are two one-place buffers. Should be a two-place buffers. So let's have a look at the semantics. So what you see is, okay, now there are two puts possible. And this is actually what you get. So this is a two-place buffer because you can put something into the first, you can put something into the other. Once you have done this, one of them, you can put it in the other. So you see it's interleaving, right? Put, right? Or put, fine. Arbitrary order is possible. You can, once you have put in something, you can take it out. You can also put in two things, take it out. You can also do a put, take the other one out, right? So you see there's no difference which one you empty, right? And what we see is that indeed the behavior is that obviously of a two-place buffer, but it's no longer isomorphic to the one that we have seen, right? So, and the question now is, and I invite you to think about, what is the information that is lost here? Sorry, that is lost in the other, that makes it basically save states. What you have seen before is that we had this in 3 states, now we have it in 4 states, and it's an interesting question. What information is lost, so to speak, in the other two-place buffer representations that we have seen? Is there anything that is lost? Is this important? These are questions that we will discuss actually in the next bigger part of the course. So, again, this was the behavior that we have seen, right? The initial state is here. And this is no longer isomorphic to the stuff that we have there, right? And worthwhile to answer the question whether this is regular CCS. So it has a parallel operator, which is a static operator, but it doesn't appear in the recursion. So indeed, this is regular CCS. Now, let's get something really challenging, namely, what we're going to do is we're going to synchronize buffers. So the specification I will show you now first. Okay, stare at this, and then I give you the intuition.
So now it gets crazy. We now take two buffers and we put them together and we synchronize them. So what does this mean? This means now we can put something in. Okay, let's see, we can put something in. Then we cannot take it out really, but it can be passed on to the other side. Okay, and now we are ready to take it out. It's out. The pass is internal. Okay, I had to do it because there is no mechanism inside. Again, we put something in. Right, this is passed on to the other side. And now we can put in some more. So we can put in actually two, right? We can take this one out, pass the other one, and we take it out too, right? So this is what we can do.
So if we try to understand what's happening, let's try to explore carefully the semantics. And I again invite you to prove the transitions by means of proof trees using the semantics that is displayed on the bottom of this page. So we start here, right? We start with that initial behavior. Okay, and then what can actually happen? Well, pass, we will not see pass, right? Because this will be turned into tau by the synchronization rule. Otherwise, it would be restricted, right? We will not see pass. So this one cannot happen. The buffer right cannot do anything, but the left buffer, it can do put. Why not? So you will basically see that in order to understand this behavior, you will have to look up with the restriction rule some action that is not of this type. Then you will, with the parallel left rule, you will go into this one. And then with the recursion rule, you will go here. And then with the prefix rule, you will find the put. And that will allow you to derive that put goes to that expression. And well, here now there's a pass exclamation mark. Buffer R has a pass question mark. Cool. So internally, you can pass the element in the buffer from the left to the right. Okay? So now you see the left buffer is empty. The right one has the piece. Okay? It has been communicated from left to right. And then it can be taken out. The get means it can be taken out. Yes? So you can use this if you want as a one-place buffer. You put something in, it's pushed over, taken out. Right? Or you can put something in, this is moved over, now something else can be put in. This is the second element that can be put in. And then the buffer is actually full, but once you take it out, right, the one in the right you can take out, then okay, the other one can be pushed over and you can take that one out. That's the behavior. So this is how it looks like in our Psycho tool. And you see there is one interesting abbreviation. So formally, you would have to write into this set pass exclamation mark, pass question mark, separate by a comma. Now we abbreviate that because it's anyway, you know, one of the restrictions for this set of actions to be restricted is that they must occur as pairs. So we basically, when we write here some action label A, we mean a question mark and a exclamation mark at the same time. Okay, and now we can explore the behavior here as well. I guess you are not so surprised anymore that this then looks like this, right? So let's reorder this a bit. So that's the behavior. And we can again look at the actions. And we now see that the actions are actually different because you have internal actions in between, right? Which come from the pass. But of course, the internal actions are internal, and there's not much of a reason to see them. And if you take this out, you see actually that the behavior looks very much the same, even though the transition system here is not at all isomorphic to any of the ones that we have seen, right? I mean, isomorphism will require you to somewhere have a transition labeled tau also in the other transition system that you're comparing with. But the other examples that we have seen had no taus. All right. So what we learn here is that the answer to the question, are any of these buffers isomorphic? The answer is yes. There was a pair that was isomorphic. I invite you to find back which one it was, but several were not, right? But, well, except for the first one that was a one-place buffer, it seemed like all the others were two-place buffers, right? So this seems to say that isomorphism is a bit too strict, basically, right? This is one thing. Now, they are, as I said, they are similar. For instance, if you look at the action sequences that we will call traces in a while, they look very much alike. But remember, we have only seen example traces, right? So now, of course, you can generate different traces, like you can have put tau get, 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 and so on. But you can also have put tau, put get tau, and so on. So you can, I mean, you can have a lot of elements in this set of traces, right? It's obviously an infinitely large set. And now, okay, we could say that two buffers are the same if they have the same traces. We still would have to deal with the tau and so on, right? And indeed, we are going to explore this next. This will be a big topic in the next part of our theory fragment of the lecture, so to speak.
So here now comes a larger example of what one can do with CCS. So this will now be a communication protocol fully specified in CCS. So it has a sender, it has a receiver. So let me try to make this drawable. It has a sender, it has a receiver, and then it has a medium below for the transmission of messages in both directions. So it has a medium for the data, and it has a medium for acknowledgements that acknowledge that data has been correctly received. So to the outside, we will only see puts and gets. So it looks a bit like a buffer, and we will understand in what sense. So we can do put, and then essentially magic happens that is not visible, right? And there will be then a get, and then there will be probably a put, then a get, and so on and so on and so on. So that's what's going to happen. So let's first have a look at the sender, what the sender does. The sender, if he receives a put from the outside, he says send to to something, right? And then it waits for an acknowledgement to travel back to the sender. Okay? And if that has happened, it can accept the next put, right? So you can think of the semantics of this process, only it has like three states. Sender is the initial state. What else do we have? Well, we have a receiver, and the receiver is essentially the same, right? Just that it doesn't have a name there, but it receives something. Hopefully it receives a message. Then it waits for someone to get the message, and then he sends the acknowledgement that the message has been delivered correctly. Now, acknowledgements travel and messages travel in two media. So we have a duplex medium here. We have a duplex medium here for the two directions. And one direction is, well, for the data, so to speak. So it accepts the send that comes from the sender, right? And turns it into a, hey, receive on the receiver side. And the same for the acknowledgements. It accepts an acknowledgement that is sent by the receiver and then turns it to an offer to receive an acknowledgement to the sender that will be accepted there. Okay, wow. The whole protocol now is putting all these together. So putting the duplex medium together with the sender and the receiver, right? Sender, receiver, duplex medium, and then make sure that nothing comes out of this except for put and get, which means we want to enforce synchronization between send, receive, send acknowledgement, and receive acknowledgement. And you remember that this is an abbreviation that we also use here. So this means send question mark, send exclamation mark, receive question mark, receive exclamation mark, and so forth. Right? Now, why don't we have a look at this? So here it is in our favorite tool. Okay, so the same specification. Here are all the entries of the function gamma are there, the bindings, and you may wonder whether this is indeed regular CCS. Okay, and the exclamation marks here give you indications about what parts may not be regular CCS. And then the question is this risky? And the answer is not necessarily, because if we are in regular CCS, then things are guaranteed to be fine. But if we are not in regular CCS, it doesn't mean that we are doomed to be bad, right? It's not forced to go worse. It's just we are sure if we are in regular CCS. And here we are slightly above regular CCS, and you can think of this if you want a bit more. So what does happen now if we explore the semantics? Let's first generate some random paths, right? And let's hide the internal steps. And what you see here is, whoop, this looks like a buffer. And if you look carefully, you see actually it looks like the behavior of a one-place buffer. But maybe this is just a coincidence. Not really, actually. So you see, why is it a one-place buffer? Because put and get strictly seem to alternate. Strictly seem to alternate. Put, get, put, get, put, get. So there is no put, right? Which would be an indication that it is more than a one-place buffer. But of course, these are just example traces that are computed randomly, and there may be some that we miss, right? So let's probably instead explore the semantics. Let's do that. So, so what is happening here? So we are here in the original state. There's a put. Then this is the send. I think this is the receive. This is the right. We can actually go over it. We see it's the receive. You look at in the corner here, right? There is somewhere there in the corner here. You should look. Then we get more information about what we actually have here. This is the receive. Here's the get. This is the send acknowledgement. This is the receive acknowledgement. And wow, we are almost back to the original state. There comes the put. And then, okay, we are going in a circle. So actually, the semantics of this expression, right, this relatively long expression protocol under all these bindings that go in the function gamma is, okay, put, then there's a number of taus, then there's a get, then there's a number of taus, then there's a put, then there's a number of taus, get, put, get, put, get, put, get, put, get, right? So this is what we actually get. And we will learn over the next 2 weeks what this button does to your transition systems. I will not explain this for now, but it shows you that the minimal equivalent representation of that relatively complicated protocol that ensures that messages are transmitted is actually just the behavior of a one-place buffer. Okay, but for sure it's not isomorphic anymore. So this is what we have here. Now, just for the fun of it, let me play a bit with this. Let's now assume that our protocol is unreliable, or let's say that the medium is unreliable. Let's assume that the medium here, if it sends something, it may deliver it to the receiver, right? This is one option. Or it may say, well, internally, I distort it, right? And then I deliver something that is bad. Okay? So this is now an unreliable medium, and we can see we can look at the random path if you want, right? And you see, wow, once a message gets distorted, the system halts. right? It stops basically. Why that? Well, if it's distorted, it's able to receive another send, but all the others are waiting for the signals. For instance, here the receiver is waiting for the receive in order to send the send acknowledgement, but the sender is waiting for the receive acknowledgement in order to make the next put, right? And then the send would come. So this is not a broken system, right? And if you want, we can also do this, explore the semantics, and we will see that once the message gets lost, right, which is over there, once the message gets lost here, this is the I. I'm sorry, I should say that. The I is our way of writing tau, because we are too lazy to write tau on a keyboard. We write I for tau. I should say this. And the I then internally turns into a tau. And this is the I where then the distort happens and then things are lost. Now, but we could have a more clever way of handling this. So the more clever way would be to let the receiver actually see that there is a distortion. I mean, assuming that's possible, right? That he can see that there is some garbled message. So he would see distort. And then, in this case, he would send a no acknowledgement, right? And would wait for something to happen. But this is only for the case that there is a distortion, right? So what you see here is that we now have either there's a distortion, then he sends a no acknowledgement. Okay, now the sender is prepared here for a receive acknowledgement or for a no receive no acknowledgement, right? And if it receives a no acknowledgement, then what would it do? It would just resend the message. The message didn't arrive, so it resends the message, and then it waits again for the sending, right? It waits for one of the acknowledgements. So it may not be that messages get lost in a row. What we have to make sure is that, first of all, we have a medium that can actually transmit this. An easy way of doing that would be, for instance, that the acknowledgement medium can also handle the negative acknowledgements. I hope this is correctly okay. Receive ACK medium. So now the medium is able to either process the negative acknowledgements or the positive acknowledgements. Okay. The receiver is willing to handle that. The sender is able to react to a negative acknowledgement by resending. The receiver sees the distorted message and says, hey, something went wrong, I cannot deliver. Otherwise he receives it, right? And this match is there. So in order to get this connected, we have now to say that the distort is witnessed by the other side, that the receive negative acknowledgement is also enforced. Synchronization is enforced. This is what I'm doing here, right? I'm saying, let's enforce synchronization on the new actions so that to the outside things are actually invisible, right? So this is what I'm proposing. And if I have not made a mistake, what do we see then? Let's have a look. I hope I have not made a mistake. So what we see is now again there's a put get. And I have made a mistake. There is something wrong here that I have to find out. So I fix a few typos. The first one is this should be an exclamation mark because the exclamation mark belongs to the, right? This exclamation mark should match the question mark here. Then there's a typo here, receive, and there is a typo there. It should be that. And maybe this now works. Yes, it does work indeed. So what do we have now? We have here a protocol where you put in some data, then it travels over the channel. It may get distorted. No, sorry, this is the I, right? This is the I of the distortion. That this is this tau here, or the I. Then comes the send no acknowledgement, receive no acknowledgement, retry. Lost again, distort, no acknowledgement, retry, no, and so on and so on and so on and so on, right? So this here is always resent, and once it does arrive on the other side, there's a get, and there can be a new put. Okay, amazingly, what we have now achieved is a protocol where messages can actually get lost, and instead, if they are lost, they're resent as long as needed until they arrive. And again, if you look at the behavior from a certain perspective that we have to find out what it actually is, it is not different from the behavioral perspective to that of a one-place buffer. We can also see this here from the actions. If you look at a random pass, for instance, and you hide the internal steps, it is just an alternation of put and get, and put and get, right? So back to our story, what we have seen here is we actually have first seen this kind of protocol, and then I have kind of freehand extended it to a version which even can handle errors in the message handling. And I hope you saw that this is relatively useful. At the end, we see that we have actually achieved a kind of complicated specification of something that is just a one-place buffer. But remember that now the put and the get are on entirely different sides, right? The put and the get are not on working on the same toilet paper. They are working on, let's say, the put can happen in Hawaii and the get can happen in Saarbrücken, right? So that's the power here that we have. Okay, to conclude what we have just seen, so I hope I have convinced you that regular CCS is useful. So basically we can write complicated protocols in this language, and at the end they turn out to be distributed ways of writing things that are somewhat simple, but of course the precise connection we have not entirely understood, namely in what sense is this complicated thing actually the same as that. Now this will be the topic of our next bigger part. I do look forward to that. I hope you do too.